All right. Good afternoon, everyone. I guess the first thing that I wanted to announce, inspired by other faculty and also TAs who pointed this out to me, is you shouldn't feel compelled to come to lecture. There is this pandemic that's happening, maybe. So we are recorded. Feel free to watch the webcast if you feel safer that way. And maybe it is honestly more prudent to do so, since we don't fully understand the scale of what's happening with the coronavirus. And the second thing is, I did look at the, mid-semester feedback that about a little less than half of you submitted, about 330 of you submitted that online form. And there were mixed responses on live coding. It seemed like the vast majority of people appreciated live coding and thought it helped them learn. There was some minority who were kind of indifferent. There weren't that many people who thought it was worse than being on the board. Most people were either, yes, it's better, or it's similar to being on the board. So what I'm going to do is I'll still live code this lecture. We're finishing dynamic programming today, and then on Thursday onward, we're going to move back to non-live coding, just on the board. So we're going to do a bunch of dynamic programming problems today. Last week on Thursday, we looked at Fibonacci, and we also looked at shortest ST path in a DAG, in a directed acyclic graph. So I want to pick up from the last thing we did, which is shortest path in a DAG. We defined a function, f of t, where f of t is the length of the shortest path from S to t in some graph, some underlying graph G. You can think of S as being fixed. S is some global variable here. And we noticed that f of t satisfied some recurrence relation. So the base case is that either t is S, so in which case the length of the shortest path is 0, right? It's not going to be negative because it's acyclic, so there's no way to get from S back to itself in negative time, okay? Because there's no cycles. The other base case is that nothing goes into t. The in-degree of t is 0. If that's the case, then there's no way to get from S to t, so the answer is infinity. I'm using infinity to denote there being no path. And then the last case, which is the recursive case, is that t is not S, and there's at least one thing that points into t. And the point there is, well, any path, the shortest path, but any path, has to go to some vertex and then go to t as the last hop, right? So break up the shortest path into the very last hop, which is going into t from some vertex q, I don't know what q is, and then the rest of the path is going from S to q, right? And this is basically just brute force search. We're saying, well, we don't know which q is the best q on the way to the short, which q is the best q to be the previous vertex in the path, in the shortest path to t. So we loop over all possibilities for q, and then pick the best one. If we choose to use q, what's the cost of using q? Well, we have to get to q optimally. That takes f of q length. And then we have to follow the edge from q to t, which takes wqt, right? So you can implement this recursion, which we did. We saw in class last time that to implement this recursion, you want to work with the reverse graph, because you want to be able to easily iterate over people who point into t as opposed to out of t, which is the out edges of t in the reverse graph. And this was an example we were working with. So let me go back to live coding. And the thing I want to show you right now for this problem is, because you already saw code for this problem, right? What do you think you might want to know about shortest paths in a graph, right? You don't just want to know the length of the shortest path from S to t, but you want to know what is the shortest path from S to t? What is the actual path? Where do I go? Okay. And what I'll show you is that you can modify the code. It doesn't change the asymptotic complexity. You'll still get a linear time algorithm. You can modify the code to return the path. And it's very similar to, I guess, other things you've seen. Basically, there's some optimization going on here where you're optimizing over the choice of q, what's the best q to use, okay? So what are you going to do in the recursion to remember the path? You're going to remember which q did I pick, which q actually achieved the minimum. So I'll have two tables. One will be the mem table like last time, which stores the length of the shortest path. But I'll also have another mem table. I'll call it the choices table, which remembers which choice I made to achieve the minimum. Namely, which Q did I choose to achieve the minimum? Okay, so let's take a look at that. And another thing that I saw, which of course makes a lot of sense, many people in the mid-semester feedback said, can we have the code so that like we can run it on our own computers? And yes, we'll make the code available this week. It'll be on the website. Okay, so this is last time. We did Fibonacci just recursively. It was really slow. Then we memoized Fibonacci. We did bottom-up Fibonacci, and then we saw you can space save on the bottom-up Fibonacci and use only a memory table of size 2 instead of n. This is the graph that's right there on the board. And this was our shortest path in a DAG memoized code. Okay? So now what we want to do is actually return the path and not just the length of the shortest path. Okay? And this was just an example of a graph that illustrated that if you don't memoize, the runtime can be really bad. So that was discussed last time. So this is the thing I want to implement. I guess another thing I realized from the feedback is it seemed like not everyone could easily read the code. So I'm happy to zoom in. Raise your hand if this is a good font size. Raise your hand if this is not a good font size. Okay. No one raise your hand for not a good font size. But just to be safe, I'll zoom in one level deep. Okay, so I zoomed in a little bit more. Okay, so okay, good. So we want to actually find the path. So what I want this code to return is a list of size 2. The first element in the list should be the distance, the shortest path distance. And the second list should be itself the path. And the path itself is a list of like the vertices I visit in sequence. So the first thing I'm going to do is just copy over the code from before, because that's a good starting point. It gives me the distance, it just doesn't give me the path. Okay. So let's put this here. And then actually, I think, this is not ideal in terms of size because it doesn't show the whole thing on the screen. So I'm actually going to zoom out again one more time. So let's find shortest DAG memo. Find shortest DAG memo. Okay. So I said that we need to have another table that remembers the choice. So this is the table that remembers the actual length of the shortest path. I need another table that remembers the choice. Choices equals none times len of g. And I'm going to feed that in here as well, feed both tables in. And then this is going to actually return to me the distance, the length of the actual distance between s and t. But then I want to recover the path. Okay? So we're going to do that later. But before we do that, let's modify the recursive code to actually keep track of the choice we made. So what's going on in this recursive code? There are two base cases, right? So we said if we're already at s, the length of the shortest path is 0. The other thing is if there's nothing pointing into t, so look at the reverse graph and look at the adjacency list for t in the reverse graph. If there's nothing pointing out of t in the reverse graph, meaning there's nothing pointing into t in the original graph, then the shortest path length is infinity. It's impossible. If I've already stored in my memoization table, I already know the answer. Otherwise, I need to actually compute the answer. So here what I'm going to do is I'm looping over all possibilities for who points into t to go there before. So for each, so let's say q is e0, right? And the weight is e1. So I'm potentially going into q. And then I say, look, if find shortest DAG memo. So this is like, I could say, let's just give this a name. X. X is equal to find shortest path DAG memo, rev g, s, q. So I'm going into q, mem choices. If x plus the weight is less than what I'm currently think is my best solution, then my choices should remember that. It should say, actually, the best way to get to t is to go through q. And the way to do that costs me x plus weight, right? Which is exactly what's going on here. and then I return memT. Okay, so that's it. The only thing I changed is I added this line to keep track of the choices. Right? What choice did I make? I chose to go through Q because it's the best choice so far. Okay, so now let's actually reconstruct the path. So first of all, if the distance is infinity, it's impossible to do it. I'll just say that there is no path. So return, distance, and like the empty path. It's impossible. Otherwise, so I'm going to work backwards. Remember, I'm trying to get from S to T. So I'm trying to get to T. The recursive call to T figures out what's the Q that comes before T. And then from there, I figure out what's the Q prime that goes into Q. What's the Q double prime that goes into Q prime, et cetera. So I'm starting at T, and I'm working my way backwards to S. So I'm reconstructing the path from S to T backwards. Okay. So I'm currently at T, and my path so far is the empty path. And I say while I'm not at S, while I haven't reached S yet, path.append T. Okay. And then where did I come from? I came from at is equal to choices T, right? Yeah? Oh, yes, sorry. Path.append at is equal to choices T, and then I think that's basically it. Okay. What? Oh, yeah, sorry. That's the, good. Okay. And then I should append at the end also S. And then now I'll reverse it, because I constructed the path in reverse order, so I'll reverse it, and then return now distance and path. So let's see if this works. I think I need to compile some code beforehand. Let's define the graph and the reverse graph. Okay, so of course this always happens. So find shortest path diagonal takes 4 arguments, but we get 5, of course, because it has to also take in choices. Okay. So what this is saying is that the length of the shortest path in G from 0 to 4 has length 11, and it's the path 0, 1, 3, 4, which I believe is correct, right? So the shortest path from 0 to 4 is 0 to 1 to 3 to 4, which has total length. That's actually a 7, not a 1. 11, the other path would have taken me, I guess, 13. So this is the shortest path. Okay. So that's that. Okay, so that's an example of reconstructing the solution. And now, basically, for DP, I feel like the more example problems you see, like the better you get at it. So I want to do a few more, on the order of 5 or so more DP problems. And I think for the next few, I want to first do it on the board, and then we can code it if we have time. So, okay, so more problems. Were there questions about that? Yeah.
So this is like the equation that we have.
Yeah.
It also holds in any graph, right? So we can't just solve it that easily iteratively if it's not a DAG, right?
So okay, so your question was this recurrence for f, doesn't it hold in any graph, not just the DAG? So why do we need it to be a DAG to do this? Is that the question?
Mainly is the DAG only helps us to easily go from the base cases to the whatever.
So actually, we'll see this later. We're going to arrive at Bellman-Ford based on this kind of line of thinking. So why can't I just do this for arbitrary graphs? Why do I need G to be a DAG to do this? And the reason is that I'll have a cycle in my call graph of the function, right? If I had a graph, that's a good question. Like if this is S, and let me just make some cycle up. Actually, let me not do it like that. So look at this here. So let me give these other vertices names. Okay. So if you try to compute the shortest path from S to T, right? So we work backwards, right? So we know that f of t depends on, basically there's going to be a min over all the things that point into t. There's only one thing that points into t, which is a. So f of t is going to depend on f of a. F of a is going to depend on f of s, but it's also going to depend on f of b. So f of a depends on f of b, but f of b depends on, it depends on f of c. C points into a. So a depends on c depends on b, but then that's going to call a again, which is going to call c again, so you're going to get infinite recursion. Okay, so we're going to see, basically there is a way to fix that, and the way to fix that is basically to do Bellman-Ford. And Bellman-Ford, as I mentioned this I think last time, I said it, but I didn't actually show you why. Bellman-Ford is just itself a vanilla DP. It's nothing special, okay? You can basically define the appropriate function f, write down a recurrence relation, throw in memoization so it's fast, and then instead of implementing it top-down with recursion, you implement it bottom-up, and then you basically get Bellman-Ford. And then once you do bottom-up, you realize you can save memory, and then once you save memory, you really have Bellman-Ford. So I'm going to say that. I'm going to give more details later in lecture as to what exactly I mean when I'm saying all this. Yeah.
How does this runtime compare to Dijkstra's or the naive version without the memoization?
You said okay. So you said how does this runtime compare with Dijkstra? How does it compare with the recursive version where you don't memorize? So the recursive version where you don't memorize, we did talk about this last time. We said suppose you had a graph that looked like this. Basically a bunch of diamonds in a row. I didn't draw the edge directions, but imagine all edges point down. This code is really just doing brute force, right? Brute force search. It's looking for, to get to t, what are all the ways I can come into t? And then for that, vertex right before, what are all the ways I can come into that, right? It's just brute force search. So if you have n diamonds, that implies you have something like, I think, 3n plus 1 vertices. Let's call it d diamonds. Then you have 3d plus 1 vertices. So n is 3d plus 1 here. Okay. How many ways are there to get to t? Basically, for each diamond, you can choose to either go down the left edge of the diamond or the right edge. So there are 2 possibilities per diamond. So there are 2 to the d possibilities, right? So there are 2 to the d st paths. And 2 to the d is basically something, it's approximately 2 to the n over 3. Right? So if you don't memoize and you just run this recursion on that graph, your running time would be something like 2 to the n over 3. Right? So it's exponential time. And it could, you could actually make it worse than that if you make it a denser graph. How does it compare to Dijkstra? This is a linear time algorithm, if you memoize. It's n plus n time. Dijkstra, it depends on, Dijkstra at the end of the day, you need to use a heap, a min heap. And it depends on which min heap you use. So if you just use a binary heap, you'll get a runtime like m log n. If you use a Fibonacci heap, which we didn't talk about in class, you can get a runtime of m plus n log n. Either way, it's not going to be linear. Okay. I know I wasn't, I didn't cover, I think Professor Chiesa covered Dijkstra. One thing I will say about Dijkstra, I like to say these kind of historical notes. If your graph has integer weights, okay, there is an algorithm due to Thorup that actually can solve single source shortest paths in linear time, m plus n. But it's out of scope of this class. Right? Again, this is making use of the fact, I say this often, that your computer can do more than just comparisons. Right? It can do bitwise XOR, it can multiply ints and stuff like that. If you take full advantage of that, you can actually get a linear time single source shortest paths algorithm, which is what Thorup did. Any other questions? Okay. Okay, good. So I want to do more examples. Another example, longest increasing subsequence. Okay. So what is this problem? Your input is some array of numbers. for example, 1, 3, 2, 7, 4, 5, 6. And what you'd like to do is you'd like to find a subsequence of this array. This is an ordered sequence, right? An array is an ordered sequence. A subsequence of this ordered array such that all the numbers in that subsequence are increasing. Let's say, for the sake of today, strictly increasing. Okay. A greedy algorithm wouldn't work. A greedy algorithm would be like, as long as I can take the number because it's bigger than what I've taken so far, I take it. If I did that, I would take 1, then I would take 3, then I can't take 2 because it's smaller than 3. Then I would take 7, I'd be done. So I'd have a subsequence of length 3, right? 1, 3, 7 is length 3. It would be better to actually not use the 7 and do 1, 3, 4, 5, 6, right? Or 1, 2, 4, 5, 6. Then I would have an increasing subsequence of length 5, right? So the optimal solution here would look something like this. Does that make sense? So how can I use this whole memoization DP idea to solve this problem efficiently? Okay. So again, whenever you have these optimization problems and you suspect that DP might be useful, I always recommend just write down some kind of brute force search in such a way that the number of inputs that you're feeding into some recursive function is bounded, and then you memoize. Okay? And then later you can think about turning it into bottom-up DP if you want. So here's what I'm going to do. I'm going to define a function f, let's call it last I is equal to the length of the LIS of the longest increasing subsequence in the array A, where I'm only allowed to use the numbers from the ith entry onward, okay, such that all numbers I pick are bigger than A last. Right? Because in my brute force search, what is the brute force search going to do? So it's going to walk over the array, and at every point in the array, it's going to say, let me take this element or let me not take it in my subsequence. And then recursively see which one's better. So as I'm doing the recursion, I need to remember what is the last element I took. Because I need to make sure that the next thing I take is not smaller than it. That's why I'm remembering what the last element I took was. And then if I'm walking over the array, that means at every step, I'm basically advancing where I'm at by 1. Right? So initially, I'm allowed to pick it. Initially, I'm considering should I take item 1 or not, so I is 1. Then after I make that decision, I say should I take item 2 or not, so I is 2, etc. We can write a recurrence relation. So f of last I is equal to. So what's the base case? The base case is I've finished processing the entire array. There's nothing left to decide. So the base case is that I is equal to n plus 1. There's no array left. And then the answer is 0. There's nothing I can take. 0 if I is equal to n plus 1. Right? If I is equal to n plus 1, I'm saying look at the suffix of the array from location n plus 1 onward. That's empty. That's the empty array. There's nothing. Okay. Now, in the recursive case, there are two options. I either include AI in my LIS, or I don't include AI. And then I just recursively try both and see which one's better. Okay? Now, I don't always have both options. If AI is less than A last, right, then I'm not allowed to take AI. So, if AI is less than A last, then I'm forced to skip I. So the answer will just be f of last I plus 1 if AI is less than A last. Okay. Otherwise, I am allowed to consider taking it. I'm allowed to try both possibilities. And then I'm trying to find the longest increasing subsequence, so I'll return the max of the two possibilities. So the max of two options. One option is that I don't take it, which is just this, f of last I plus 1. Right. And then the other option is that I do take it. And if I do take it, then my sequence got longer by 1. So 1 plus, and then now my last is I. The last thing I took is AI. And then I'm allowed, now from now on, I'm allowed to use things from I plus 1 onward. Does that make sense? Questions? So now let's try to analyze, if I were to memorize this, what would be my memory requirement, my memory table size, and what would be my runtime? So remember, this whole memoization business is I need to have a spot on my table for every possible input to my function. How many possible inputs are there to f? How many possibilities are there for last? N, right? So last is remembering what's the last thing I took. There are only n things. There are n possibilities for last. I is where am I currently in the array. There are also only n possibilities. So n squared memory for my lookup table. Now for any given input, for any combination of last and I, how much time do I spend computing the answer? Ignoring the recursive call. Constant time, right? So ignoring the recursive call, I do an addition here. I take a max. I mean, I'm just doing like 2-3 steps. So the time is something like, here you could say, it's at most like the number of inputs times the time per input. This is constant. This is n squared. So the time is O of n squared. Okay. Now, can I improve the memory? These are all, whenever you see a DP problem, I always recommend going through these 3 steps, right? 1, define some function in words. 2, figure out the recurrence relation. 3, analyze the runtime in the memory. And then the question you should ask when you talk about memory is, if I did bottom-up DP, could I improve the memory? Okay. And the answer in this case is yes, right? Why? Because if I plot the memory table, let's say this is the memory table. So here I'm plotting, let's say I is here. So I is like a different row of this table. And then last is a column. And these are the entries of my table. Okay. What's the base case? The base case is when I is equal to n plus 1. So let me number these. So let's say here this is I is equal to 0, 1, 2, 3, or I guess 1, 2, 3 up to n plus 1. And then last also is anything between 1, 2, 3 up to n. Okay. The base case is when I is equal to n plus 1. So all of this stuff is the base case. Right? So if I'm doing my bottom-up DP, the first thing I do is I'll just fill that top row with zeros in my 2D array. And then what does f of last I depend on? It depends on f of last I plus 1, and it also potentially depends on f of I plus 1. So if you look at any entry here, it depends on f of last I plus 1, so it depends on the thing right above it. It also depends on potentially something else, which is also in this row. Well, I guess Right, so I guess it depends on I plus 1, which is basically something that's like 1 off the diagonal. But the point is, all the answers in this row only depend on the previous row. Or like again, all the answers in this row only depend on the previous row, which means when I'm filling out this row here, I only need to keep this row in memory, and everything else I can just throw out of my memory. I only need to keep 2 rows of the table in memory at any given time. And then when I move on to the next row, I can throw the thing that was 2 rows in the past. Okay? So bottom up, can get away with roughly 2n, which is O of n, extra memory. Instead of n squared. Okay? So this is an example. It's not always true, but this is an example where doing things bottom up actually improves your memory. Okay? Questions about that? Yeah. It would still be n squared, because you would like at the end of the day, what do you want, right? Oh, I should have said that up there. So when you write down that function f, you should also always ask yourself, like, what do I want to call f on? So what do I want to call f on here? I want, for example, the max over all I between 1 and n. I don't know where the LIS is going to start, right? So I'll just try all possibilities for where it starts. So the max over all I from 1 to n of 1 plus f of I plus 1. Does that make sense? This would give me the answer. If you want to be slightly clever, another thing you could do is, before you call the recursion, just prepend minus infinity to a. So I mean this in like Python speak. So take the list that only contains minus infinity and add a to it. And then what I want is f of 1, 2. Does that make sense? So the point is, this is just a hack to not have to take a max over all these things. It's the same. The point is, what I'm saying here is, what's the length of the longest increasing subsequence? Only using item 2 onward, where all the numbers have to be bigger than item 1. But item 1 is minus infinity, because I added minus infinity. And everything is bigger than minus infinity. So basically, any increasing subsequence would be OK. Sorry? Yeah, here it's one. Yeah, here it's one indexed. Yeah. Any other questions? Yeah. In the runtime? What about it? The number of inputs. Oh, well, we said there are n possibilities for last. There are n possibilities for I, or n plus 1 possibilities for I. So the total number of inputs is roughly n squared.
And that was a top-down implementation.
This is a top-down implementation. That's right.
How do we switch to the bottom-up?
Yeah, so maybe let's do a bottom-up. Maybe I'll switch to, I'll live code it. Okay. Live coding is always risky, because I might have a bug, but you know, you have to live a little. Okay, so okay, good. So let's just do here. I'll just do bottom up since that was the question. So let's do list bottom up. Okay. So if I were to do a bottom up, let's first not try to optimize the memory. Let's just use n squared memory. Okay. So mem is none. So let's say n is the length of L. Now it's 0 indexed. It's not 1 indexed. And also, let me do the trick of prepending infinity. So mem is equal none times n for in range n. So let's say now mem last I gives us f last I. Does that make sense? Okay. And what do I want to return at the end of the day? I want to return mem. So last is 0 because now it's 0 indexed. So I want to. The last thing I chose in my LIS was the 0th element, which is minus infinity, and then everything I pick after that has to be bigger than minus infinity. Okay. So that's mem 0, 1. I'm allowed to pick items from 1 onward. So first, let's fill in the base cases. The base cases are when I is equal to n. Remember, we're now 0 indexed. So yes. But I'll just pretend that the array is actually 1 bigger now. The question was, shouldn't I subtract 1 because minus infinity isn't really there? But actually, it is really there because I just put it there. So I'll just pretend it's there. So let's fill in the base cases. So the base cases are when I is equal to n plus 1. So for last in range, I guess n, mem last n plus 1 is equal to 0. That's the base case. And then I say for x in for I in range. Okay. Actually, and I didn't remember my Python. So you want to like decrement by 1. Sorry. But I think you can also do range. Yeah. So you can reverse, but you can also do like range. I think n minus 1 or something like that. What? 0 n minus 1, something like that. Is that what I want to do? I want to start, n 0 minus 1. Right? Actually, yeah, so maybe I shouldn't have. What? N minus 1 minus 1. So let's see. Okay, actually, let's experiment because my Python is rusty. So range 10 minus 1 minus 1. Let's say list of that. What do I get? Okay, good. So that looks good. So I want to go down from n down to 0. That's what I want to do. And I want to do minus 1. That's good. So good. We're good. So now what I want to say, so I have two options, right? Either I'm allowed to take this element or I'm not allowed to take this element. Okay? I'm not allowed to take this element if L of I is less than L of last. I'm not allowed to take this element. So that means that mem of last I is just equal to mem of last I plus 1. Otherwise, or less than or equal to, let's say. Otherwise, if it's bigger, I am allowed to take it. And then mem of last I is equal to the max of mem last I plus 1. And 1 plus mem of last I plus 1. And the other choice is 1 plus mem of I plus 1. Right? So I think this is good. Maybe. So let's see if this actually works. List bottom up. What? Last is not initialized anywhere. That's a very good point. So yeah, so I need another loop over last. So for last in range 0 n, or last in range n, now I do this. Okay, so now I think it's good. Maybe. So let's do list bottom up so let's do something very simple, which is just the list of numbers from 0 to 10. So the LIS should be everything. Okay. List range 10. So this is a list. This is just 0, 1, 2, 3, 4, 5 up to 9. So the LIS is everything, which should have length 10. But we got an index error, of course. So it's complaining about last n plus 1. So this is the danger of anyone see it? What should be n? Ah, yes, good. This is the base case, good. But there's still a problem. Okay, so this is very risky. Okay, so I don't want to, for last in range n, mem last of n is equal to 0. Okay. I think I basically reversed these. No. So okay, so I guess I'm off by one somewhere in something. Let's try to do this. What? Sorry. Times L? Here? No. So, okay, so I goofed somewhere in something, but basically the point of this code is exactly filling in the array, the 2D array. As I said over here, let me just move this up. I'll fix it in the code I released to you. But live coding is indeed very dangerous. So the point is just, right, so you fill in the base cases first, which is the top row, and then you basically fill in the rows going from top down. Okay, so that's what the code is doing, even though somewhere I seem to have a typo somewhere. So any questions other than like what was the typo? Okay, yeah. Are you saying what the bug is? Yeah. Okay, let's take it offline because I don't want to spend lecture time debugging too much. It's somehow less interesting to debug, even though it's of course necessary when you actually want to implement this. Okay, so that was the bottom-up implementation or some approximation of it. I want to do some more examples before we run out of time in lecture. So let me do another problem, which is problem 3, edit distance. If we have time at the end of lecture, we'll go back and find that bug. I really hate having bugs linger around. So what is edit distance? Edit distance is I have two strings. S 1 up to n, it's a length n string, and t, which is an m length string, a length m string. And I want to compute the fewest number of edits to turn S into T. What are the allowed edits? So one allowed edit is insert a character into S. 2, delete a character from S. And 3, substitute one character. One character in S for another. Okay. So as an example, So let's say S is kitten, and T is equal to sitting. So one thing I can do is I can substitute K for S. Then I can substitute this E for an I. Then I can insert a G. In fact, this is the cheapest way, under these three allowed operations, this is the cheapest way to turn kitten into sitting. So the edit distance between these two strings is 3. I would like to compute for any given strings the edit distance. Okay? Okay. So here's the idea. The idea is, look, I'm trying to turn S into T. So I know that after I've done my edits to S, in particular, the first letter of S has to match the first letter of T. Okay? So what are the different ways I can make the first letters match? So here I have, let's say, S, and then some stuff. And then, so that was what? Kitten and sitting. So let's say kitten, KI whatever, sitting, SI whatever. So what am I saying are the options? One option is I can insert an S right here. That's one option, right? And then if I do that option, I recursively have to, and I recursively have to make these two things match. So this is insert. Another option I have is I can delete the K. If I delete the K, then I recursively have to make this match with this. So delete first letter of S. And the last thing I can do is I can substitute. So I can say, look, there's Ki whatever, there's Si whatever, and then I can just substitute a K for S. And then I recursively have to change this into that. So those are my three options, right? So now I can write down a brute force search. And as I do this recursion, what changes? Basically, I'm either going to advance one letter in S, or I'm going to advance one letter in T, or I'm going to advance one in each of them. So I'm always going to be keeping track of some suffix of S and some suffix of T. So that inspires the following definition of a function. F of ij is equal to the edit distance between S from I onward and T from J onward. And what I want is I want F of 1, 1. Does that make sense? And now we can write down a recurrence relation. So F, let's write down the recurrence relation. F of ij is equal to, so what are the base cases? One base case is that S is the empty string. And then the cheapest way to turn the empty string into T is just to add the letters of T one by one. So adding letters of T one by one is going to cost you m minus j plus 1, because that's how many letters are left. M minus j plus 1 if I is equal to n plus 1. If I is equal to n plus 1, there's no character left in S. It's the empty string. Similarly, T might be the empty string. And the cheapest way to deal with that is to delete the letters of S one by one. To delete one by one instead of insert one by one. So deleting one by one costs n minus I plus 1 if j is equal to n plus 1. So this handles the case where, so this means S is the empty string. This means T is the empty string. Okay. Now in the case where neither is the empty string, I can actually do some kind of recursion. And I'm going to basically try all those three possibilities. This was substitution. So I can either do substitution, delete the first letter of S, or insert the first letter of t before s. So what are the costs of those? So, so let's say the min of, what is the cost of insertion? I have to insert, that costs me 1 plus f, and then now I still have to recursively turn si onward into t, but t is now j plus 1 onward. This corresponds to inserting the first letter of t before s. I can also delete. If I delete, I'll have 1 plus f of I plus 1j, because I deleted the first letter of s. Okay. And the other option is substitution, which costs 1 plus f of I plus 1 j plus 1. And this is if, there's no point in doing substitution if the first two letters are already equal, right? So, so actually, let's replace this 1, which it's either going to be 1 or 0. It's going to be 1 if the first two letters are different, because then I have to actually do a substitution. But if they're not different, then doing the substitution is free, basically. It costs 0. So this is, let's just call this, I don't know, delta ij. Delta ij just means if, delta ij means it's 1 if si is not equal to tj, otherwise it's 0 if they're equal. So this is otherwise. Okay, so 2 base cases in the recursive step. Questions? So we have the function, we have the recurrence relation. Now what about the runtime and the memory? Memory. How many possible inputs are there? How many possibilities are there for I? Right, so S is a length n string, T is a length m string. So how many possibilities are there for I? N, right, because I is an index into S. And there are m possibilities for J, so it's nm, extra memory for the lookup table. And how about the runtime? Well, per input to F, I'm just doing constant work and taking a min of 3 things, right? So again, it's constant time per input. There are nm inputs, so it's O of nm. Now, if you look at the dp table, right? Here you have the i's and here you have the j's. So this is an index into t. So this is between 1 and m, 1, 2, up to m. And this is, let's say, 1, 2, up to n. What did we just say? We said that some entry, ij, it depends on ij plus 1, I plus 1j, and I plus 1j plus 1. So ij depends on ij plus 1. It also depends on I plus 1j. It also depends on I plus 1j plus 1. Right? So basically, that's what the dependency looks like. F of ij will call these 3 recursive calls, which means that everything in, say, this row only depends on other things in the same row and the previous row. Right? So you can just remember your row and the previous row at a time, and you can get away with O of m memory, 2m memory. You can also say everything in this column only depends on its own column and the previous column. So you can also choose to remember the last 2 columns, which means 2n memory, right? So you have 2 options. You can either do column by column or row by row. One of them costs you m memory. Row by row costs you m memory. Column by column costs you n memory. Which one should you do? Whichever's less, right? The min of m and n, right? So you have the input. You have s and t. You know what m and n are. So if m is smaller, you'll choose to go row by row. If n is smaller, you'll choose to go column by column. So with bottom-up DP, you can get O of min of M and N memory. Okay? That's an M. Okay. Questions? Yeah. Yeah, top-down in memoization, you would have this bit. You'd have the full MN lookup table, right? Yeah. So, one of the main advantages of going from top-down to bottom-up is that for some problems, if you have this kind of structure where one row only depends on the previous row, or like column depends on the previous column, or whatever, bottom-up you can save memory that way. Is there any advantage to top-down? For me, as you saw with me trying to implement LIS bottom-up, I'd make typos. So I personally am a recursive thinker. I think about everything recursively. So it's easier for me to reason about. Not everyone is that way, I know, but for me, it's easier to reason about things from a top-down point of view. And usually for me, once I have the top-down point of view, then I can kind of try to work backwards to implement it bottom-up. So if you think similarly to me, I guess that could be an advantage. Another advantage is, so you might have a problem where it's not a priori obvious so you have some like complicated recursion and it's not a priori obvious like what subcalls you'll eventually make. Like what inputs you'll eventually call f on. So you could implement memoization where your lookup table, your mem table, is actually a hash table. And then your memory size will only be proportional to the inputs you actually recursed on. Right? So maybe you could imagine a problem where in principle there are like tons and tons of possible inputs I could call my function on in the recursion, but for whatever reason, my recursion doesn't actually have a path to most of those things. Okay, so then now my memory will be proportional to the things I actually touch that go into my hash table, okay, which I could potentially save from. So that's another way in which memoization could be better, depending on the problem. But what I just said now is not true of the problems we've been talking about. So I still want to do a couple more examples. Let's do another classical one, which is problem 4, I guess now, is knapsack. So our input is a list of n items with weights wi and values vi plus a capacity capital W. Okay, so what should you imagine? What does this problem represent? I have some backpack or a knapsack. Okay, because of the material I use to make this knapsack, if I try to pack too much stuff in it that's too heavy, my knapsack is just going to like rip apart and die. So I can only fit W pounds of stuff in my knapsack before it breaks. Okay, and there's and I'm robbing a bank or something or a store. And different items in that store have different weights, and they have different values, right, if I resell it on the black market. And I would like to pack as much stuff in my getaway knapsack as possible to maximize the dollar value of what I'm packing. Okay? And the question is, like, how can I maximize that dollar value? So example, let's say my weights and values, I have 3 items maybe. My weights, W1, W2, W3, are equal to, let's say, 11, 10, and 10. And my values are equal to, let's say, 15 and 10 and 10. A natural thing to try might be, like, take the thing that has the most value per pound. Oh, and what's W? W, let's say here, is 20. So a natural thing would be like take the thing that has the most value per pound. and maybe greedily do that. Then after you take that, take the next thing that has the most value per pound, right? Until I can't fit anything anymore. Notice here, item 1 has the most value per pound, because its value per pound is 15 over 11, whereas these have value per pound 10 over 10, which is 1. So the greedy algorithm that takes the thing that's the most value per pound would choose item 1, and then it'd be done, because it can't fit items 2 and 3. And it would get a total value of 15. Whereas if you chose items 2 and 3, you would actually get a total value of 20, which is better. You can actually prove that the greedy algorithm always comes within a factor of 2 of the best value you can get. Okay? Notice that 15 is within a factor of 2 of 20. But we're not going to talk about that today. We're going to try to come up with an exact algorithm that gets the right answer. And we're going to do it using dynamic programming, of course. Okay? So let's do it. So steps 1, 2, 3. Step 1 is I'm going to define a function which is f of iw is the max value I can pack in a capacity W knapsack amongst items I onward. And what do I want? I want f of 1 capital W, right? Because I'm allowed to pack items from 1 onward. That's everything is allowed. And my initial capacity is capital W. That's the input. And I can write down a recurrence relation. And the point is, again, it's based on brute force search. I'm just going to walk over the items one by one, consider item 1, consider item 2, consider item 3, etc., one by one. And for each item, I have 2 choices. I either take the item or I don't take the item. I recursively try both possibilities, and I see which one is better. Okay? So what's the recurrence? So f of iw, little lowercase w, is equal to, what's the base case? The base case is, for example, there are no more items left, in which case the best value I can get is 0. So 0, if I is equal to n plus 1, there are no more items left. Otherwise, I can either choose the item or not choose the item. Now, am I always allowed to choose the item? No, because the item might be too heavy. It might not fit in my knapsack. So if I'm not allowed to take the item, then the best I can do is f of I plus 1 w. That's if, so I don't even consider taking the item. That's if the item is too heavy. If the weight of item I is bigger than w, I can't actually fit it. Otherwise, I have 2 options. I can either take the item or not take the item, and I take the better of the 2. So it's the max of f of I plus 1 w, that's not taking the item. And the other possibility is that I do take the item, and then I get its value. So I get its value vi, and then I get the value from packing what's left optimally, which is f of I plus 1 w minus wi, right? Because I packed item I, so I have wi less capacity in my knapsack now. And that's otherwise. Okay? So how many possible inputs are there to f? There are n possibilities for I. There are capital W possibilities for lowercase w. Because lowercase w, as I recurse, is always going to be something between 0 and capital W. Right? So 3, the memory is like n times w, and the time, for each possible input, I do constant work. So the time is also O of nw. Okay? And again, the answers for I only depend on I plus 1. So I only need to keep 2 rows at a time, the current row and the previous row. So bottom up implies I can get away with O of W memory, not NW memory, if I do the space-saving optimization of only keeping 2 rows at a time. OK. Is this a polynomial time algorithm, by the way? Is this, what do you think? Who thinks this is a polynomial time algorithm? Who thinks it's not a polynomial time algorithm? Who has no idea why? Who has no idea? Okay, so in this class and in general, in life, when people say polynomial time algorithm, what they mean is that the running time of the algorithm, let's say that the length of the input is L, then the running time of the algorithm is a polynomial in L. It's bounded by, let's say, O of L to the fifth, or L cubed, or whatever. Okay. Now, what is the input to knapsack? It's a list of n pairs, wi's and vi's, as well as a capacity capital W, right? So what's the length of the input? How many bits does it take to write down capital W? It takes log of capital W bits, right? So this part of the input to write down capital W only takes log of capital W bits, but my runtime depends on W, which is exponential in log W. So this is actually an exponential time algorithm in the input length, okay, if W is big, right? Imagine that capital W is like a trillion. Writing down a trillion only takes, I don't know, 12 digits, okay? But I'm actually going to take a trillion time steps. So this is what's called, just some jargon, a pseudo-polynomial time algorithm, because its runtime depends on the size of the numbers and not log the size of the numbers. So this is not actually a polynomial time algorithm. Okay. But if the weights are small, if someone gives you an input where the weights are all bounded by poly n, it would be a polynomial time algorithm. Okay. So, but in general, it's not a general polynomial time. Yeah. No, but there are actually, so you said, couldn't I make the same argument for n? Writing down n takes log n bits, right? But I'm not actually writing down n. I'm actually giving you n items, right? Like the input has an array of length n, and each one of those is a pair wi, vi. So that part of the input actually has length n. In bits, it has length at least n, because I have n pairs of numbers. And then I have this extra int w, which takes log w bits. So the total length of my input is proportional to something like n and log w. So to have a polynomial time algorithm, I would want to be polynomial in n and polynomial in log w. But here I'm not polynomial in log w, I'm polynomial in w. So it's actually exponential time. So just something to keep in mind. Later in the course, we're going to talk about NP hardness and NP completeness, et cetera. This is not a polynomial time algorithm. And in fact, knapsack is what's known as NP hard. Okay, we don't actually have, in general, efficient algorithms for knapsack when the weights can be large. Did you have a question?
Best way possible, only take constant memory, but you still have to, if they tell you, like, give me, Fibonacci number 100, that only takes log 100 to write, but you have to do 100 steps to get there.
That's right. So that's right. So your question, so you're saying, if I say compute the nth Fibonacci number, it's not a polynomial time algorithm because it took me something like n steps. But the thing is, depending on if I phrase the problem as give me the nth Fibonacci number, then you really can't help it not being like, okay, so n only takes log n bits to write down. I want an algorithm that takes poly log n time. But the problem is that the nth Fibonacci number itself has n digits. So it's kind of hopeless to expect an algorithm. There is no algorithm that takes poly log n time because even the answer takes n time to write down. So it's kind of a hopeless lost cause. Yeah.
Typically, when the input is a number, you think in terms of the number of bits used to represent.
So yeah, so here if it's like, so what you could say for Fibonacci, for example, is like imagine that the input n is like written in unary, right? So I'm happy to have an algorithm that runs in poly n time. But again, if you insist that you have something that runs in poly log n time, it's impossible. Unless you say something like, give me the nth Fibonacci number mod 1,000. Right? Then actually there is an efficient algorithm. Okay, so I want to do just a couple more examples before I let you go. So we did knapsack. I want to do two things. One is shortest paths. You've already seen Dijkstra. You've already seen shortest path in a DAG. You've already seen Bellman-Ford. I want to do Bellman-Ford, but I want to do it with our newfound powers of like the way we think about memoization, and show you that Bellman-Ford is just very similar to everything we've seen so far. And then I want to show you an exponential DP. So let's say shortest path. So problem 5. So here the graph is not a DAG. So I think you asked me earlier, can I run that previous recursion on a graph that's not a DAG? And I can't because I'll have infinite recursion. So here's what I'll do instead. So the goal here, let's say it's a directed graph, and I could have arbitrary edge weights. So positive or negative. And let me assume that I promise you that the graph does not have negative cycles. So the goal is compute the shortest path from S to T. So one, let me define a function. F of let's say bk is equal to the length of the shortest path from S to B using at most k edges. Okay. Why did I do that? Because I want, as you'll see, like I want to avoid having a recursion that's an infinite recursion, and basically by introducing this k, I can avoid that. Okay. And the point is, if there are no negative cycles, right, then there's no reason to ever use a path that has more than n minus 1 edges in it. Because if you have a path that has r edges in the path, how many vertices are on the path? R plus 1, right? So if you have a path that has more than n minus 1 edges, so it has at least n edges, that means there are at least n plus 1 vertices on the path. But there are only n vertices in the graph, which means if you have n plus 1 vertices on the path, you cycled somewhere. But I promised you this graph has no negative cycles. So there's no reason to cycle. Okay? So you never need to consider paths that have more than n minus 1 edges if the graph has no negative cycles. So what I want is f of t comma n minus 1. This is the length of the shortest path that uses at most n minus 1 edges. Not exactly n minus 1 edges, because the shortest path might use fewer edges than that. And I can write down a recursion. I can write down a recursion that says f of bk is equal to, the base case is that, let's say k is equal to 0. I'm not allowed to use any edges. If I'm not allowed to use any edges, well, then either the answer is 0 or infinity. It's 0 if k is equal to 0 and b is equal to s. I'm already at s. Otherwise, it's infinity if k is equal to 0 and b is not equal to s. Okay. So now let me look at the recursive case where I'm allowed to use at least one edge. If I'm allowed to use at least one edge, then there's that last edge that goes into b. Again, that edge had to come from somewhere q. First of all, let me say that I'm allowed to use at most k edges, which means I'm also allowed to use at most k minus 1 edges. So one of the things I'm allowed to do is min of f of b k minus 1. I don't have to use the kth edge. And the other thing is loop over all vertices q that point into b. So the min over all q such that qb is an edge of the weight of the edge from q to b plus getting to b in at most k minus 1 edges. This, by the way, is Bellman-Ford. Okay? If you were to implement this bottom up and then notice that bottom up you can save memory, you would basically arrive at Bellman-Ford. Okay. What's the memory? There are n possibilities for b because b is a vertex. I initially called k being n minus 1, so there are n possibilities for k. So n squared. What's the time? So naively, you could say, again, there are n squared possible inputs. For each input, I have to loop over all the q's. There are at most n q's. So I could get n cubed, n squared times n. If I'm a little more careful, just like I was with shortest path and DAGs, I could say, look, fix k. There are n possibilities for k, right? So there are n possibilities for k. And then let me sum over all b's, and then the time for fbk. What's the time for fbk? It's proportional to 1 plus the in degree of b, because I loop over everything that points into b. The sum of the in degrees is exactly the number of edges. So this is O of basically m plus n times this n because of all the different k options times n. So basically mn time, which is Bellman-Ford. Okay? Yeah. Yeah, Q. Okay? And again, with bottom-up DP, you can observe that the answers for k only depend on k minus 1. So I can only keep, I only need to keep 2 rows or 2 columns or whatever at a time, just the current k and the previous k. I can get away with linear extra memory instead of quadratic extra memory, which is exactly, basically like the dist array in Bellman-Ford. Okay? This is exactly Bellman-Ford, right? And if I want shortest paths, I might have to do the very last one at the beginning of Thursday. Actually, I'll do 2 at the very beginning of Thursday, but I do want to do 1 more right now, since we're becoming pros at this. Another way to do shortest path, let's say all pair shortest paths. So in Bellman-Ford, in shortest path in a DAG and Dijkstra, there's always like a source vertex S, and I want to know how to get from S to everywhere else as fast as possible. Suppose I want to know all pairs. From all S to all T, what's the shortest path from S to T? I could just loop over S and then do Bellman-Ford from each S separately. Each Bellman-Ford takes me mn time, and then there are n possibilities for S. It's m times n squared time. M could be as bad as n squared. So that could be an n to the 4th time algorithm. I'll show you an n cubed time algorithm called Floyd-Warshall. So basically I want to know all shortest paths between all pairs. So I'll define a function f ijk, or let's say stk, is the length of the shortest st path when the intermediate vertices in the path must be in the set 1 up to k. Okay, it's kind of a clever thing. Oh, and what do I want? In an arbitrary path, the intermediate vertices are allowed to be anything. So what I want is f of stn, because the intermediate vertices should be allowed to be anything. And then I can write down a recurrence relation which is that f of stk, the base case is again k is equal to 0, which means I'm not allowed to have any intermediate vertices. And if k is equal to 0, I have to get from s to t without any intermediate vertices. So that's just the length of the edge from s to t. So that's the weight from s to t if k is equal to 0. Otherwise, I can either choose to use k or not use k. If I don't use k, I have f of stk minus 1. So I'm allowed to use things between 1 and k minus 1. And if I do use k, then I have to go to k and then from k to t. So f of sk k minus 1 plus f of kt k minus 1 otherwise. Right? So I can either choose to use k as one of my intermediate vertices or not. If I don't, this is not using k. And if I do, that means at some point I go to k, and then from k I go to t. And that's it. What's the memory? N cubed. N possibilities for S, N for T, N for K. What's the time? Also O of N cubed. Because for each input, I do constant work. And if I do bottom up, notice that the answers for K only depend on K minus 1. So again, I only need to keep track of the previous and the current K. So I can cut down the memory by a factor of N and get O of N squared memory. Okay. So that's it, and we're going to continue. I'll finish off 2 more DPs on Thursday, and then we're going to switch topics.